and say welcome to lecture number 4 in parallel and distributed computing in the summer term 2025. So today we have a relatively central lecture. Maybe in a few seconds. Yes. Oh no, it's Konstantin. So we have a relatively central lecture because we are talking about the message passing interface. This is also what we are mainly using in the homework later, and which is also most central part of the exam, obviously, and hopefully what you are going to use in the rest of what you take out here for the rest of your life, because this is why we are coming here in the first place. So message passing interface. I now stop writing things down. I'm using a little bit PowerPoint because we are talking about code, and when I write code by hand, that's getting to be a little bit annoying. However, just I have to say this in the beginning because we have a written exam without computer in front of you. In this exam, you will have to write code by hand, so get used to it, okay? So, message passing, like many things in programming, is not necessarily best learned from this kind of lecture where I stand and make the monkey here, moving around. There are plenty of online resources that you can take a picture, which you have apparently just done, where you get tutorials on learning what MPI is. So I'm trying to explain to you, but maybe using online resources is even better than listening to this lecture. I don't know. Anyway, we'll talk about this today. So message passing interface is something already I would say rather old, not as old as, for example, C or Fortran, but it's been around since the 90s. And it is now, for a very long time, the actual method how we use parallel computing on distributed memory machines. So there is other methods that we use in what is the opposite? The shared memory machines. We'll come to this later lecture again, but now we're talking distributed memory machines. So every node has their own access to their own memory. And this is so we use this here with C and C++, but there's also other implementations in other languages for the same thing. But we'll concentrate here on the C implementation of this. So there are a couple of iterations. The last one that I've written here is from 2012. I guess that there's always getting new stuff somehow included, and there may be something newer. But this is not. We don't need to study the detail of the very latest versions. It is an industry standard. That means it is not a software per se. So it's just a specification how software would be written, and therefore there will also be different implementations of the thing. And these different implementations, they try to implement the standard, but they are not necessarily 100% compatible and not necessarily doing 100% the same thing each, right? Because it's a norm, it's not a software, it's a norm, and a standard. And so you will So for example, Intel and Microsoft, yeah, they have implementations of this standard. And they are not absolutely compatible necessarily. The two main things where this is used for is the point-to-point communication and the collective communication, which you can see like here. So point-to-point, you have different machines, which in this abstract settings are called ranks. Yeah. So you can also have several ranks on one machine, yeah. But say the ranks are the independent incarnations of your program running. So the different ranks are present, and the point-to-point communication would be if one rank communicates with another rank, yeah. Saying you send a signal to or data to a specific neighbor, one-to-one communication. The other thing is, so that would be like, one sends something and one receives something, and another possibility would be collective communications. This is where, for example, one communicates with everybody else. Yeah. There are different. Each time there are different ways of doing this, which to this detail we come in a minute. So, in principle, how it works is that all these processes that run in parallel always take the same program. Yeah? And this is important because obviously they are supposed to do different things. So in one and the same program, you have to somehow specify who is doing what, right? But it's all in one program because they all run the same program, yeah? So now the way you decide on what is doing, so what process is doing what is, you decide this according to what I just said is your rank. Yeah? So each process has a process number that we call rank, and it knows its own rank. So it can decide according to its rank what part of the work it is supposed to do. Yeah? So what you always have to do is you have to include the header, MPI header, and then you start the program, and then they run on different machines. Important is the variables that the machine has are always local because we are talking explicitly with distributed memory, right? So all of them have their own memory, meaning when they initialize, if they use variables, their variables are all they are all local to that particular incarnation. And they differentiate only by the rank. And here, for example, would be something like a minimal program, yeah, which, okay, I haven't decided. Maybe we step over it. We could also implement it now, but I mean, maybe. Did we do this in the past? I think we'll just. Do you want to implement it and see? I mean, it's just typing this up. Yeah, maybe we implement the other program later. Okay, well we go and implement the other thing. It just go over this here. So this would be a minimal MPI program. So we'll have some output. So we'll have includes standard I/O, yeah, so that's not important. That's why I have it here in the grayish kind. Important for MPI is that we include MPI header, yeah, and then we start this int main. So what can you explain what this here actually means? Int argc char arg. Do you know what that means? Yeah. So what are these? What will end up in argc and argv? So okay, you don't know. So these are used for the command line arguments. So in this argc, int argc is the number of arguments that have been given on the command line. So when you get they are separated by spaces. Yeah. So here you get the number, and then you get the pointer to the character arrays that are the actual command line arguments. Yeah. So by this you can access to the command line arguments. Then you have this MPI. So okay. Then we have some variables, and there are two variables that we usually need to use. Two minimal information that are important for us. This is the rank that we have, which is the ID of this particular process. In this case, we call this my ID. You can give this any name that you like. You could also say this is my rank, yeah. But here it's now called my ID. And then there's the number of processes, because these are the two things that are usually important. So you have to know who you are, because all they run the same. Okay. So you're born, and then somebody comes to you and tells you your name is this. Yeah. So do that, right? So you have to know who you are, and usually you also have to know how many others are there. Yeah? So these are your name, the number of your neighbors, okay? So, and then you have to initialize. You always have to initialize the MPI process, and this takes these two arguments, and what we usually do here is getting just sending the command line arguments off. Yeah? And I have to admit a little bit, I don't really know why we are doing this. So usually if we don't put command line arguments, they would be empty. Konstantin, do you have an explanation why we sent there the command line arguments to, so we can specify the number of yeah, so you could send some information to the MPI via the command line. Yeah. So, but if you don't specify, you don't need to specify anything, because then you're getting 0 here, and then it just initializes like a default version of MPI. Yeah, which inside this lecture will be sufficient. Yeah. But it's something that takes these two arguments. So one thing that you observe right away here is that what MPI is usually doing, and this is why Konstantin also gave this introduction, we are passing arguments by reference. Yeah, that's very common in MPI. Yeah, so these functions, these MPI functions, they are of the type void usually. So they, not all of them, but usually they are, we don't catch their return value. Rather, we pass arguments by reference, and then they will modify these variables that you send by reference. So this is in particular important for the next two commands here. So, these two commands are also ones that you always need to do. There's an MPI com size that gives you the size of that, you know, communicator environment that you are using. Yeah, you have to specify in what communicator, in what is this called, the I want to say sphere. I mean, communication environment you are. Yeah. So there is a global communication environment that is MPI COM world. So this is the thing that you just initialized. So we are all talking together. So this is inside this include MPI. This is already specified. So you don't need to introduce this. So this is already there, right? So MPI COM world, and then you hand this the reference of the number of processes. So what this will do is, because it got the reference, it will write the number of processes inside this variable. Yeah. So this is the way you are usually using MPI functions. You are not taking a return value of the function, calling the function, getting a return value and write this in the variable, but instead you are sending off the reference and it will modify the variable that you sent. The same thing obviously with my ID. So here we are asking for the personal rank of that particular process. So, and then all we do is the usual hello world. So we take this printf function for writing out like my ID, yeah, and the number of processes. And once we have done this, we have to, clean up, yeah. So we have to finalize the MPI environment, so to close this MPI world. Okay, so and now how to run this? Okay, we come to a demo later. This is where we'll just go through it now this way here. So we need to compile this, and for this, now this is of course something that depends on the MPI implementation that you are using, and as I said, this is an industry standard, so there are different implementations. Yeah, but the one that we use on Phoenix uses this compiler, which is basically a C++ compiler, MPI C++. Yeah, so and then everything works as usual. You get the C++ file, you specify an output, and then you get this, okay, we call this output, and then also we have to, once we have this, we have to run this in the MPI environment. So we have to write MPI run, and then we have to specify the number of processes that we are using. So for example, if you use 4 processes, we specify number of processes np minus np4, and then we run the app. And then all of them give us some result here, and because they you see, they are not running in any particular order, yeah, because they all run in parallel on that machine. Okay. Any questions? No. Okay. Should be pretty simple. So then the basics. There is, of course, I mean, like, we are doing this for 30 years, MPI, so there are plenty of different functions, but there are only a few that we absolutely need. And most, okay, not okay. So there was no communication actually in this hello world, I have to admit, yeah? So communication comes okay, we come to communication right now. But the important things that we need are these here. And I notice now that I said nonsense. Konstantin did not intervene, but I said nonsense. When I said these functions are of type void, they are not of type void, they are of type int. So you get some like, I think they actually have a return value, but this return value is I guess something like a status, and it's often not. I mean, usually we don't catch this return value, right? So because the way we deal with this is passing variables by reference and then getting this modification. So the thing that we always need is the initialization, otherwise we are not using MPI at all. Then the other two are, something that I think you also always need. There may be very specific examples where the size of the system doesn't matter, I don't know, but usually you will always need the size of the system. So they always need an MPI communicator, and usually this will be MPI com world, if we have only one. And then it takes a pointer to an integer, which gives you which indicates to you the name of, not the name, the size of the system. And in the case of the second function that you always need, the rank, it gives you the name of yourself, so that you know how you can distinguish, how the process can distinguish itself from the other processes, which is very important. So then getting stuff done is then, so this is now very minimal, is to actually send and receive stuff between processes. So these are actually the important things. So how this works, we have an MPI send function that sends data, and the way this is done is to use a pointer to void data. So pointer to void means you are not specifying what your data is. What you're actually doing is you are specifying where in memory your data begins. It's just, an address in memory, okay? And because you just say where it begins, you also have to say, in principle you would have to say where it ends, but this is not convenient. Therefore, you do it in a little bit different way. You specify how many items you are going to send. This is the int count. And then you are specifying of what type you send so many, right? So then now you told it where does the data begin, how many items you send, and on what type they are, and then the process by taking the number of items and obviously knowing the size of the items, it knows how much it has to send. This is the way it knows this. Then obviously we have to send the address where we are telling the address where we are sending it to. So this is the rank of the receiving process, right? And then there is something that we are not going to use in much detail in this lecture. This is the tag. So we can give an additional information how to handle this when it arrives. Like this is if you like think this is you are sending a letter to an address, then you may write a small note together, give this to that and that person, right? So this is something This is an additional information, one integer, that you can, in your program, use internally to distinguish between these things. Because the tag here has to match when you send something with a tag, then you're receiving only when you wait for the same tag. Yeah, so I mean you cannot just use an arbitrary number here, though these two things have to match. Yeah, so and you can use this for internal distinction. You also always need to use the communicator, because you may have different communicators. So you may have different, you know, you could be in different worlds at the same time. So different post systems, if you like. Okay, so that would be send. So you send stuff off, and then there's the other side that is receiving this, and this works pretty much the same way. So data has to be written to a specific place in your memory here. So you get data is again a pointer to void. You get a count, and you get a data type from which it knows how many bytes it is expecting. And then, so this is different from your from your post office. So if you send a letter to your post office, so the other guy who's receiving it does not need to specify I'm waiting for this letter. Yeah, here you have to actually specify I'm waiting exactly for that letter. Yeah, so I'm waiting for data from there, and this data has to come with that tag. Yeah, to make an internal distinction here. And then again, there need to be the communicator. And there is one more thing for the receiving part, that it specifies a status. So for example, you know, because maybe the thing was not sent, then the status would be failure, yeah, like this. So we get here again additional information. Okay. Then when we are done with our program, we have to close the world down, which is done by MPI finalize, and this is just using void. So then we are done. Okay, so these are the minimal set of functions that we need to do MPI. This communicator, as I've already mentioned, if we do not, you know, split up our world, which we can do with MPI com split, yeah, but this is something I mean, during this lecture, I've not found any application for this, so we'll always use only one communicator. So for us, the communicator will always be MPI com world, yeah, so we'll always communicate with everybody. So we'll basically, whenever there's an MPI com, we'll use MPI com world. And then there are these different ranks, and the only thing that you have to remember with the ranks is that they start from 0. Yeah, so the lowest process comes from rank 0. Yeah. Okay, and usually the rank 0 is, I mean, in practice, this is not required, but in practice, the rank 0 is usually treated in these programs in a special way, and because there's always the stuff, I mean, in all the programs, there's always some serial stuff, yeah, stuff that you want to do only once, and then you have to assign these to a specific process, and then it makes sense to let rank 0 do this, because rank 0 is the one that is always there. Yeah, so there's not necessarily a rank 10, because you allocate only 9 ranks, then rank 10 does not exist. Whereas when the program runs, there will always be a rank 0. This is why in MPI programs you will usually see things like if my rank equals to 0, do this. This is something that happens a lot in MPI programs. Yes. So you have to, what did I want to say here? Of course, so you have to include MPI.h, yeah, so that there are the functions, data type, macros, and so on. You always have to call this function in the main, because otherwise there is nothing, the initialize, otherwise you cannot use MPI, so this is always what you have to start with. So usually you need to know how many ranks in your process are. This is, or not in your process, in your entire program is. This is why you always need to call MPI com-size, and you usually need to know who you are yourself, because otherwise all the programs would do the same thing. So this is also what you have to do. In MPI finalizes is to close things. So this is always what you have to do. And there are a few constants that are defined in MPI.h. The most important of which, because we use it the most often, is this MPI convert. Yeah, that's just a constant that we are using. Okay, and as I said, ranks start with 0, and on Phoenix we compile with MPI C++. Those are our basics, more basics. Yes, this MPI init provides this world, which I indicated like this, where we have the different processes which are indicated by their different ranks, and the ranks start from 0. Okay, I think I've said this now 3 times, so maybe it's come through. Okay, now, right, the data types. You may know, or maybe not, that the C standard does not actually provide definitions of the size of your data type. The reason for this is because the C language is supposed to stay as closely to the machine language as possible. Yeah, and if, as in other programming languages, some other programming languages where you have a very strictly defined way of, a float has this size and behaves like this, then the programming language has to make sure that the thing behaves always the same way. C programs do not necessarily behave the same way on different machines. And the reason for this is because they are basically calling the machine as directly, the machine functions as possible. And so they rely on what is implemented on the machine. So if, like is actually the case for very common processors, like the like Intel processors, that they do operations on 80 bits instead of 64 bits. Yeah, so they may actually use different data types. That's not exactly IEEE, double sense. So this is, C does not necessarily specify this, even though it's very common that they have a certain size. MPI actually does this, so it specifies the length of data type and also specifies their own data type. So this is, we have them all with MPI char, and you see here, because they are all in caps, these are constants. Yeah, so, and they are defined in MPI.h. Yeah, so actually they're just numbers. Yeah. So this is the thing. These are the things that you use to specify what type of data you are moving around. Yeah, so that the communicator is able to know what amount of data it is sending. So we have MPI char, MPI short is 2 bytes, MPI int, yeah, so this is compatible to, you know, in C we distinguish between signed and unsigned, but this doesn't change the size of the data, obviously. So this would be a signed int, then there is a long signed long int, so this, for example, would be 8 bytes. Yeah, that's a thing that's not necessarily in C++ the same thing. MPI unsigned char, unsigned short, unsigned, so unsigned is an unsigned int, unsigned long. Unsigned long int. Oh, I hope this is not a mistake. I don't actually know where I got this from, but because MPI long is 8 bits and MPI unsigned long is 4 bytes. Konstantin, can you look this up whether we made this correct? Okay, maybe. Currently, I'm just a little bit surprised about that one, but the others, and there's a float of 4 bytes and a double of 8 bytes, and the MPI long double that we don't know. Do we get any results of what an MPI unsigned long has in size? Okay, I mean, it depends on the compiler. Okay, so there's also not okay. So I just said that MPI is better than C++, but maybe not. Okay. Now let's try to understand how this works. So later we're going to talk about shared memory. We already talked a little bit about shared memory, yeah, but now we are talking about distributed memory. So every process has their own memory, and now the question is, how do we actually move things around in practice? So in practice, and this is something that may happen, you know, without your actual knowledge. Yeah, so MPI is doing this for you. You want to send something, some data, so it takes this data and puts this in its own outbox, if you will. That's the send buffer. Yeah, and now okay. I need to be sure that I'm saying the right thing. No, actually you're specifying a send buffer. So now this is taken out, yeah, by the MPI and put into its own memory, then sending it over the network, yeah, and then it's being unpacked on the other side and put into the receive buffer, then you can then use for further processing, yeah. So there's always this many copying things around. So you always have to specify, we'll send this and we receive this, and then you have to put this into the place where you want to have it. All right. Yeah, then, as I said, there is 6 functions that we need and 500 functions that we could use. Yeah, so because we may have, they are not all always useful for the same thing, and we have to distinguishing between some of their properties. In particular, there is blocking and non-blocking communication, and then there's also synchronous and non-synchronous communication, but this is a bit more complicated. So blocking and non-blocking is that if you have a blocking communication, I mean, if you have a blocking function call, also in other cases, so this this function is, so you call this function, and then this function returns once it's done what it has to do, yeah? And a non-blocking function is a function that you say do this, and then it returns and leaves some process in the background to actually execute what you want to have. Yeah. So, and these things so these things are here differentiated. So the very basic send and receive is blocking. So this means it is returning once it has, pushed. For example, the sending is returning once it has pushed the data off. It is blocking, but, and we come to this later, it's not synchronous. So basically it's saying, so I put the stuff in the letterbox and I send it off. So it's not waiting whether it was received. Yeah. So we need to be more specific for this. It is said I'm done sending, but I've not checked whether it has been received. Yeah. In the case of non-blocking, it does not even wait until it is done sending. It just tells the computer, send this. Yeah, it's like if I put something to the desk of my secretary and say, so send this away, I'm going on, and the other one is I'm actually putting this into the post, so I know it's gone off, yeah, but I've not checked whether it has been received, yeah. Because this, let me see whether I have this on the okay, yeah, why we are so specific here. So when the sending is done, so I have this blocking send. What I can do is I can use the buffer with which I was sending stuff yeah, I can change this, yeah, because the letter is in the box. Yeah? The letter is already in the box, so when I on my side change my variables, this will not modify the variables that I've already sent. Yeah? Even though I did not look whether they have already arrived. So this means I can, after send is complete, I can modify this. Whereas when I have this I send, so instantaneous send, then instantaneous send or instantaneous receive, I'm not sure that this has already moved into the letter box. Yeah. So I cannot overwrite my buffer, because when I overwrite my buffer in between, before it is sent off, it may send off the wrong thing, right? So these are the differences here. Right. So in the receive version, there as in the receive function, there is also the status, where we can specify an MPI status. If we are not interested in the status, we can use here another constant, namely MPI any source, and then it will so it will so basically we are I'm making here a mistake. I think this should not be any source. This should be status ignore. Konstantin, this is the right one. Status ignore. Right? Yeah, status ignore. So you can ignore the status by using MPI status ignore. So hopefully this was the correct way. Okay, non-blocking communication. So communication runs in parallel with other. So this is important if you don't want to wait until your assistant put the post into the. I mean, you're watching. Did you put it in the post office? Yeah. So, in the letterbox. Yeah. So you want to do other work first. Yeah. So this is the reason why you have these freedoms. Yeah. Because this may not work right away because you're waiting for networks. Yeah, so you cannot send this stuff right away, so you can do something else while your message is in the output, so to speak. Yeah, this is, I mean, that's pretty important because as I've indicated in lecture 2 or so, and that parallel programming introduces a lot of overhead. Yeah? So you want your friend to help you, but in order for your friend to help you, you have to write a letter. You have to write a letter. You have to put this into the letter box. Yeah? They have to deliver it. They have to unpack it, and then they have to do work with that. Yeah? So you see, there's a lot of overhead, and this overhead. I mean, usually if you start trying out parallel programs, it's very likely that your first parallel program would be much slower than if you do this all in serial, right? Because there's all this overhead, and this has to balance out with the help from your neighbor. Yeah. So if you, I mean, it's like I want to move my cupboard here to there, and then then you always have to ask, so, okay, I can ask my neighbor to help me. So how much work do I have to put into talking to my neighbor that they help me, or compared to how much work it is for me to do it myself? Yeah, that's the point here. So with this non-blocking things, you of course need to know when you're actually done. Yeah. Now we come to. Okay, we are not supposed to drink in here. Okay, if you want, you can stand there, drink, take a sip. It's not just don't pour it over the computer. Yeah. I think you're not that well, right?
Yeah.
I'm sorry. So basically, you may need to know when the sending is actually done, right? So you do something else, but then you'll check, but then you want to use the buffer again later. And in order to control this, you can use MPI wait. So the idea behind this is you send something off, then you do other work, and then you come to the place where you need the buffer the latest. Yeah? Here we need it. And when the work is not yet done, then you have to wait there. So this is something that you have to be very careful with, because if you don't do this properly, your program may run in a non-deterministic way. Yeah, because, okay, what could happen is, you say send this off, then you do something else, and if this something else takes up enough time, then it was actually sent off, and then you can use your buffer again and nothing happens. So, and this runs very well 100 times, and then there is suddenly a slow network in between, yeah, so that sending gets postponed, it takes longer, and now what you're doing in between is done quicker, and now you override something, yeah, and then your program crashes, yeah. So I mean, you're familiar with operating systems, Windows, and so on, where you think, so yesterday my program worked, so suddenly Windows crashes or something. So if everything was programmed in absolutely the correct way, they would never crash. Yeah, so one possibility is that somebody forgot to wait in the right spot. Yeah, and in 99.99% of the cases, this still worked. Yeah, because there was so much work in between that the one process never overrun the other process, but there are these occasions when things just terminate in the wrong order, and then you get stuck. So the difficult thing with this is that if you make it wrong, you don't notice in 99.9% of the cases. And this is why we have buggy software, because if the software wouldn't run most of the time, then people would notice there's a bug and remove it immediately. Okay, so this is, I can predict you, this is something where in the exercise you are going to have some trouble with. I'm pretty sure. Maybe not. Okay, but most students had this. So, okay, so you can block you can put a wait here. What you can also do is you can test whether it has been done and make a decision on whether it has been done. So for example, so I mean, if you say wait, then it means you've done everything else, yeah, and now you get stuck here. If you take test, then you get, so then you know, for example, that it has not been done, but you can do something else again and test for it later again. Yeah? So this is why we have wait and test. And then we can also, if we have to wait for too long, we can also cancel it. Okay. Yes. So non-blocking. Let me see. How's it going with time? Okay. Some examples with non-blocking communication. Okay, we have the important things are always in black here. Yeah, so there's stuff that we've already talked about. I mean, there's stuff that is now specific to this program. So, for example, that we have a buffer of 20 char, and then we have my rank, and we have a tag, and we have a flag. Okay, I guess there's not completely. Oops. I mean, this program. I just noticed this program may not actually work correctly. So this is we would have to specify, for example, that the tag is equal to. So we have to specify the tag somehow. Yes, please. Also because there's no int in here. Yes, okay, we will have int and in principle at the end, but then we are running out of space here. We would usually say return 0, right? Yeah. So I mean, this is sorry for. Wait. So how's this? Return 0. Now nobody sees the closing bracket. Okay. Yes, so I was a little bit inaccurate here. I'm apologizing for this. The thing I was going to request status. Okay, I guess I mixed. I may have. Sorry, I did even more mistakes here, but maybe we'll go through. Okay, so there is. I should have made this in. I should have indicated this as being fed. Okay, so we are using MPI status, and I'm going to use to actually distinguish. I mean, the thing is we can recycle the status. Yeah, we can recycle the status, but then we have to remember that we only get the last status. Yeah, so if you don't use the status, then you don't care. But if you use the status, then the status may actually mean something else that you were expecting. So, okay, we need. So the thing is the MPI I send uses not a request but a status. Status 1 and a status 2. and I guess I will also, use this later here. Okay, we send, now what we do, if my rank is equal to 0, yeah, we send this buffer of 20 to, this is the address of the neighbor, yeah, so it's to rank 1 with the tag communicator, and we'll have the status. And if my rank is equal to 1, so, okay, then we are on the receiving side. Yeah, so then we receive this. And okay, I should not modify the program, but Konstantin, now you have to help me a little bit. I send, does this take a status or a request here? Actually, it must have a request, because otherwise how do I know, how do I stop it here? Has it a status and a request? Okay. Did I? Okay, you see, I'm messing up. So I sent. Okay, let's. Also the one has a request and the other one has no. This. No, but they also need a request, because how otherwise do I get a weight? Okay. Okay, so the status is only for the weight. Okay, sorry. We are trying to learn things together here, right?
Actually, in the previous slide.
In the previous slide, yes.
For receive, it was status.
In the, yes, but it was,
No. The slide.
yes.
The status.
This is not I receive.
Oh.
So you're not, because this is blocking, you're not waiting for this. Yeah? So this is the important difference. Yeah? So we do not need to have a request. We do not need to have a request for that, because you know what we should do with this. No. You know, if we don't know, what we should do is we should try it out. What do you think?
Yeah.
So let's go to Phoenix here and make a new file and call this file icom, because it's immediate .cpp. Okay, so now we have this. I will copy this code in here. So obviously this won't work, because we have forgotten something very important, and this is the include hash. Did I include the MPI MPI.h? So this is the minimal thing that include include. Okay, so now things get the only thing with this program is we do not do an output. So okay, the one thing that we also have to test here is that you see this MPI wait for the request 1, that is the send, will also be called by the function, by the other function. So let's just see whether this is going to get stuck. Let's go to CD. Where are we? We are PVR 2025. CD Gaia, and we are in lecture 4. And now, so what would we do? We use MPI C++, and we call that thing icom.cpp minus o icom. In function start undefined reference to main. Undefined in main, undefined reference to main. What on earth in main? In function start. What on earth is function start? Undefined reference to main. Main. Is this, you know, this is copying something from PowerPoint into that's very dangerous, because there may be some signs that are not the same. So what could that indicate? What on earth could that indicate? Icom main inchar.
Is it because we added int before main?
Wait. Okay. So I see there is one potential downfall, but I think this should this matter? I think this should not matter, but let's. That should not matter. Oh, it matters. Oh my God. Okay, so first thing you call initialize, yeah? So, and the problem is we are not going to see anything. The only thing that we may see is whether this is getting stuck or not, yeah? So MPI run. Let's say we are only using 2 processes, and I call this icom. So, do we get stuck? Or we even crash? Undefined, wait, where are we? Class default, wait. Primary job terminated normally, but one process returned non-zero. So one thing that we could, so we just to see whether waiting is working. So what we could do is to wait only for process 0 on request 1, right? And only wait on process 1 on request 2, because now we sent this with request 2, yeah? And so they don't wait for anything that they have not yet started. Let me save this. Let me try to... It did not complain about the compilation. And then let's run it. Okay, so now we have made several mistakes apparently. So we did not... Okay, so my slides are... You know, my slides are... how do I... What on earth did I do here that I don't... How do I get... no. How do I get out of this? Yes, so how do I get out of full screen?
Escape is not working.
No. How did I actually get into full screen? Okay, I mean, I can, obviously, let's do it this way, okay? So, there we made several mistakes. So let's remember to do this thing first, yeah? And let's wait. So I need this brackets here, obviously. Okay, I'm not dealing with style now. I'm just doing it this way. Okay, so you see, there's always bugs in code, yeah? Okay, we learned something hopefully now from we only learn from mistakes, yeah? Don't underestimate the usefulness of mistakes. Okay, let's have this one more thing here. Right, so I've already indicated that there is yet another version, yeah, that is the synchronous communication. That is even more blocking than blocking, if you will, because this only returns once we have verified that the data actually arrived. Yeah, so that's called synchronous communication. So it's now the one is, so you could say that the standard version, send and receive, they're kind of a little bit in the middle of the two. Yeah, so the one is, so there is one that is less strict and this here is most strict. Yeah, so as I send is less stringent, so it returns immediately, and this here will only return really when the message has been received. And there is more to them. So there is, yeah, the standard way. The standard way may use internal buffers or may not use internal buffers. That we don't really know. There is ways where you can specify that it is using buffers. Then there is the synchronous send, and then there is ready. Can be used if it is guaranteed that the appropriate receive command is already waiting. So, you know, I've never used this one. So there's even more detail how you can be very specific in what you're going to do. So I guess I have okay, so a few things that we have to see. So the message, when you send several messages, then they arrive in the same order in which they were sent. When the receiver B successively sends two receive instructions to sender A that match the same message from A, the first instruction is served first. So, this is like as first come, first served all of the time. If more than two processes are involved in the communication and wildcards are used, so any source, right, then it's not clear what happens. So, for example, so any source, yeah. So we usually have to specify where things are coming from, but you can also say, so we don't care, give it me from any source. Then the one that comes first is served first. So, and then we come to the other topic, that is group communication. So the basic group communication without really doing a lot of doing a lot of sending and receiving is if you want to synchronize all the processes, yeah. Then there is a hardcore way of doing this. This is called barrier. So if you put a barrier somewhere, and I tell you try to avoid this because this is something that people build walls when they don't know what else to do, right? So barrier is a complete wall where you hold everything. Yeah. So once everything arrived there, then they go on, right? So sometimes this is necessary, but it's not the best style because usually this, you're blocking everything, and this means everybody is waiting for the slowest process. So this usually so this can be very counterproductive if you do parallel programming because you want to have more speed, yeah, because everything is as slow as the slowest process, yeah. Okay, so but this is how you can stop everything. Then there are actually all-to-all communication things. For example, there is broadcasts. This is something, yeah, so that you could think there would be, for example, a master process that is telling everybody, so let's now do that, yeah? So some process has received or generated the initial data and has now distributed this to everybody. This is called broadcast, yeah? So broadcast, so how do we know where this is? So how does this work? So you have a buffer, which is either the input or the output buffer for you, yeah. And then you do the same thing as usual. You have a number of variables that you want to send. Then you have an MPI. Then you have this data type, and now comes the important thing, namely the root process number. This is indicating who is sending, yeah? And everybody that is not sending is receiving. So everybody has to call broadcast, yeah? But for the one that has this process number, they are sending it out, and all the others, they are receiving it. The same thing, okay? And yeah, so the other thing you can imagine, there's a communicator, of course. Then there are other communication functions. We have a small picture on the coming slides that would indicate this. So there's MPI gather, MPI scatter, and all gather, and a few more. And they work in a similar way with a root process, and where we have the root process where it's coming from, and the others are the receivers. Then there is this function reduce, which is a little bit even more involved. That is using actually computation on your data already. Yeah. So let's see. So what this does? So there's a send buffer, there's a receive buffer, count data type, and then the important thing is the operation. So there are operators that you can use on the data. Yeah, and you also specify who's the root process. So there are then 12 different operations that you can use, and examples. Okay, zum Beispiel. Okay, so this means, as an example, I don't know whether we mixed up language. Okay, as an example, so there will be the maximum, the minimum, the sum, or this kind of thing. So, for example, you're looking for the shortest path in a network. So you distribute the network over several machines. Everybody is looking for a shortest path, and then they collect all their results back. And then you want to know what would be the value of the shortest path. So you use this reduce with a minimum, and then you get out the minimum number of what everybody discovered, right? Or you solve an integral in different parts. Then you would do this with then you would sum up the parts, and then you would use MPI sum in this reduce function. Okay, so now a picture on this crew programming, as I said, in this picture we'll have here horizontally the different processes that are working, and we have the data in this column. And say, so the process A has, say, these 5 different data points. Yeah, that could be sent. So if you send, now you can do an all-to-all communication, yeah, where you send, for example, the first item to everybody, or the 0 item to everybody, so then everybody knows everything. Everything from not everything, of course, only the thing that has been sent from all the others. Yeah, so we'll have an all-to-all communication. Then all gather would do yeah, so all gather will do something very, very similar. So it will basically send the information from all the different processes to all. So the single parts of all the different processes to all the different processes. That all the processes know the same thing afterwards. Yeah. So very often this is not necessary, because if you, for example, want to make an output, then it would be sufficient that this is known only to the root process. Yeah, therefore you have rather than all gather, you have gather. Yeah, so where this is arranged only for one process. Yeah, and scatter is the opposite. Scatter is the opposite to gather, and broadcast is you send something to everybody else. Okay, I guess we are right. So, yes, this is the thing that I wanted to go through this lecture. And now the idea was, and we are roughly also in the right time, that we do a little bit of implementation, right? And try to solve a particular problem that we call ring communication, and it's in computer science. This is, I believe, known as the philosopher's problem. So, because there is, I don't remember the story exactly, but there's an idea that philosophers sit in a round table and all of them have a spoon on the right side of their plate, and so who is picking up? So there's as many spoons as there are philosophers, but if everybody is grabbing to their right side to get the spoon, so they're okay. No, I'm kind of mixing this up. Forget what I wanted to say. What I'm saying here. The thing is, if we communicate in a circle, yeah, and we have to send something and receive something, then it's of course the question, who is starting with sending and receiving? Yeah. So, and if you program this in the way this is indicated here, you may run into some trouble, and I think this is what we are trying to figure out now. Yeah, but in order to actually see this, we go out here. So, what do I have? Control F11 or what?
Yes.
No. F?
Because you have, you need FM, first type FM, and
Okay, I don't see it.
FM und dann FM, also ZFM, and then F.
11. Okay, I still don't see it, but now it's not so important. Okay, okay, the hope was we are kind of programming this together. So this is are you ready for, are you in the network? Yeah, because usually, okay, so the indication I have something a little bit prepared here. And yesterday a little bit out of time, but see whether we get this done here. So this is my stupid way I'm taking this lecture, that we write things here down.
If you don't mind me asking, can I have a 5 minutes break?
Okay, you can have a 5 minutes break. Yeah. I don't. Yeah. Stop. Am I going to stop the recording? I don't know. There is no pause. So, you will want to continue?
Yeah, sure.
Okay, so the idea behind this, I'm never sure whether this is the most didactical way of doing this, but the thing we have done this in the past is that I type something, people type this too, and then we try to, I mean, though that it goes through your hand in a sense once, yeah. I'm typing very slowly, yeah. So then this is why it should not be a big problem. So because we are, the thing that we are now going to do is we make a very basic ring communication, see that we have some trouble, and then we try to modify the program that we avoid this trouble. Okay? So, but first we'll start this. I'm typing, and in my suggestion would be that you type this too, if you are already logged in the. No, okay. So you have to. Okay, so you're not, because I was thinking that you would be logged into with your laptop.
No, actually, laptop is still unable to connect with the system.
Okay, so we have to wait for the machine to
Yeah.
boot. Oh, then we should have taken the break in between. Hmm?
Do you use MPI on your laptop?
Yeah, I use VPN.
Do you use VPN?
Yes, Cisco.
Okay. Strange. First point.
Okay, because I have to use this in my laptop too. So somehow it works for me. But I also always use need Konstantin's help. To make stuff running. Okay, so because we apparently have to wait until you set up your system. So once you are done setting up the system, yeah, because that's also what we are going to use in future, and I mean we are doing something extremely bad today because we are going to run a program on the login nodes, but the program that we run is so short that it shouldn't be an issue. I hope so, at least. So the idea is when you are logged in, then please go to PVR 2025 to your own folder, and then make a right click and make a new file with, for example, ring.cpp, right? So you have to log in, of course. I think the lowest one is the one down there is no, on the left, the lowest, yeah, here. So you have exactly. So you have to go there and see whether you are. Yes. So you are probably. Yes, you have to put in the password that you hopefully remember. No. Okay. I'll give it to you. So this is the password, but I need this myself. But Konstantin has distributed the password, right? Okay, so you need this password for your exercise, yeah? Okay. So now in this, I hope you did your own folder there already. Yeah, go to your folder and generate a file. Yeah, and because once we are done with this, we get connected.
No, still not. Yeah.
Okay, now we are here. Now you go to your, right, now you generate a file. And can you read this properly? what I write here?
Yes.
Okay, so then we go through the very stupid thing of doing synchronous typing, yeah? Okay, we'll include IO stream and then also standard IO.h. This is things that we use. And now the important thing is, of course, includes MPI.h. Include, yes. So then we do our int main with int argc. So what I told you before, this int argc is the number of command line arguments received when you call it, and the other one is a double pointer to the array of characters that are actually the command line arguments. So this is, we usually call this argv. So this is something that you see a lot in in some software. Most of the time you don't need to bother particular. Okay. Here I see, okay, let me try this out with because I believe that we don't need to call MPI init before we introduce variables. I think this can be done even before. So we'll define MPI status that we use for communication later, and we use the important things that we need is my ID. So this is something that we always need, and num processes. So these are stuff that we always need, and now we have to fill these things. So before what am I doing? So right. So we have to start with MPI. So we get all the functions here. MPI init, and this takes references to the command line arguments. So this is argc and references. Don't forget the reference, argv. Okay, great. So now we have started an MPI communicator, and now we need to identify who we are. Say this is MPI com rank, and this uses the what am I doing? MPI com rank. I mistyped this. MPI com rank, yes. So this uses a communicator, yeah? And the only communicator that we have is the communicator with the world. Is MPI com world. MPI com world. Okay, is accepting this. And now we have to catch our rank. And this we catch into my rank. So now let's see whether you're not my rank, my ID. So what else is always necessary?
Status.
No, not
Size.
the size. MPI
Is
MPI.
it okay to swap size and rank?
Okay, so if you like, but why would you do this?
No, I mean in
Yeah, so it's okay.
soil
It's
size
okay.
and
Yeah, so we can do the size first.
Is it, I'm asking, is it mandate or we can write as is?
No, you can ask for the rank and the size wherever you want. They don't need to be next to each other or something. Yeah.
Okay.
I mean, if you could, if you like, no, yeah. So you can ask for this all the time. Yeah. So again, we have to have the communicator. I find this hard to write, actually. So, and then in here we'll have to catch this, and we catch this into num prox. Wait, taking this, yes. So, never forget the semicolon. So now we know the size and we know the ID. So this is the minimal things that we have to do. So now reminding us that we want to solve this ring communication problem, meaning that we have to determine what is the destination of our neighbor. So what I'm now doing is I'm taking the destination, I call int destination. So and now we can decide whether we go to our left neighbor or to our right neighbor. Yeah. So say I'm saying the destination is my left neighbor. So what I do is my ID minus 1, right? So I call this my left neighbor. So it's the lower one. What? Okay. So of course this is nonsense. So this is my ID minus 1 is the destination. So this is where I'm going to send stuff. Now, okay. Does this always work like this? No. Why not?
It works.
It works.
Yeah.
Always.
Yeah, because we start with index 0 and we go till the end.
So, okay, when my ID is 0. So what is my ID minus 1? Is minus 1. So does this work? Okay, so how do we solve this problem? So we are on a ring. We are on a ring and say we have the case my ID is 0. So first of all, I mean the obvious is to ask whether my ID, whether my ID is equal to 0, right? So if my ID is 0, then I have to do something else, right? So then what is then destination? Well, it has to be the highest rank. So what is the highest rank? So how many ranks do we have? 4. Why do we have 4 ranks? So how do you know that we have 4 ranks? You remember how I specified the ranks? I specified the ranks. See, when I ran the last program, I specified the ranks by saying run this with 2 ranks.
Oh, got it.
So the program does not know. So yes.
0, 1, 2. No, I'm not confused.
No, I mean, like I told MPI to run this with 2 ranks. So I could have run this with more ranks. Yeah? So the program, so how do we know with how many ranks we are running? I mean, why have we done this here? I mean, look, if it was like you said that we have 4 ranks, why wouldn't I just write num prox equals 4? Right? So we don't know how many ranks we are. So we know how many ranks we have because we ask for the size. Right?
Yeah, then num prox minus.
Right. Num prox minus 1. Right. So this is why is it complaining about destination? Did I mistype this? No. Okay. So that's the that's the destination. So also we have a source, right? Where it's coming from. So source is the neighbor on the other side, right? So if the destination was my rank or my ID minus 1, then the destination is my ID plus 1, right? And then we have the opposite problem if if my ID is what? If my ID is equal to what is the end of the line here? Well, it's the other end, right? It's num prox.
Is it not source equals to num prox?
Yes, that's even more clever. Yeah. Yeah, you can write it like this. Good. So, if this is the case, then source is equal to what? 0. Right. Okay. By the way, I don't know. Now I'm typing alone. I guess I mean we can do it like this, but then later when I mean you decide yourself. My idea was you are. Because if you have to catch up, then we take longer. So we don't. Okay, now we need to do some sending and we need some data that we want to send. And what data do we take? I say I do a double my old data where I simply put, say, my ID. Okay, I'll simply put my ID into the data. And so this is what I want to send off, and then I want to receive something, double my new data, and this is, well, no, this is something that I want to receive. And then we do the communication. So MPI, so what, we start with sending. We start with sending, and my suggestion is that we are now very, very stringent and take synchronous communication. So this is S-send. S-send is the synchronous communication that only returns once the parcel has been received. Okay? So to see this version first. What we are going to send off is my old data. This is what we are going to send to our neighbor. This has the length. You see, you actually, the software is helping you here, right? So we get the buffer, then the number, then the counts. We count 1, and we send a data type that is MPI double, because we put this into a double. So we send away 8 bytes. Then we have to send the destination, and the destination is, well, what we call the destination. What we've called the destination. Then we have to send a tag. So we have not specified the tag here, but since we are not using any different tags, my suggestion is we tag everything with tag 0, so then everything will be received the same way. And then we need a communicator, and the only communicator that we can use here is the mcom world. So by this, we specified what we sent. So now we send this. Afterward, we have to receive it with MPI. MPI MPI receive. Okay, so MPI receive. So here we have to get our receive buffer. The receive buffer is now my, what did I say? My new data. My new data. This is where stuff will arrive. Then we'll see 1 MPI double, and this comes from the source. The tag, as we said, we set the tag to 0, and we use MPI com world. So, and then there's also a status that we have to take care of. So what we could use here is MPI status ignore, but because we've already set up here a status up here, we use this thing that we had. So I'm not going to use this status. So in principle, I could also say that this is MPI status ignore. Status. Is there anything wrong with this status? Yeah. There is, okay, do you see what is wrong with the status? The status comes by, right, it's not status, but it's status by reference, yeah? Okay, so I was just confused because I wrote status and, you know, it underlined it, so it was helping me, something is wrong, I did not see what is wrong. Okay, we have to send the status we have to send the status by reference because this is modifying the status. Yeah, so when this goes in by reference. Okay. Now, basically we have this and we have done the sending, we have done the receiving, and now we are going to somehow we are now going to get this out. Okay. So we've done the sending and receiving, and now we also want to do the output. So what we could do with the output is, in principle, we could now let every process do their own output. Then we'll see a chaos. What we prefer is that we have a master process that is doing the output. Yeah. For this, we have to specify something new and say that now, as I said before, there is a lot of in this kind of programs, you will often see if my rank or my ID is equal to 0. So this is something that's only done by the master process. And let's say we'll do so we'll get an output array with, say, double. So vector to double, let's call this A, and now specify a new array, new double of length, that's equal to the number of processes. Okay, so this is a way how you, because we are allocating new memory, we have to call the new function for the array. I don't know whether you're familiar with this. I'm not sure we used this in the introduction. Yeah. So and now say we are process 0. So I'll say that A0 is my new data. So this is what the process 0 has itself received, and for all the others, we now collect the data, which we do in a for loop. So we write for int process equal to 1. So we start with process 1, and p being smaller than the number of processes, p plus plus. So okay, we iterate over the processes, and we receive from all these processes our data. So what's okay? So we need something to receive the data in, and therefore I will specify a double temp here. So this is where we want to receive the data in. Okay, here, going here. So now we use MPI receive so we put the receiving part into this temp. This is our buffer. What we are receiving is one MPI double each. We get this from process P. This is our source now. We use the tag 0 because we don't care about tags. And we use MPI com world. And what I'm going to do here is I'm recycling the status variable that we used before. So I use the same status, same status, and then we are done receiving. So what we have not done yet is sending. So everybody else, yeah, like everybody that's not process 0 is now going to send. So we need an else. We need okay. Yes, we are done with. Okay, maybe before we come to the else part, we should. Okay, there's one thing that we should do because we need to see what we have done. Then we do some output, right? So let's do some output first. So and say we do basically the same loop again, but now we want to include also the process 0. Therefore, I start the loop again. Otherwise, I could recycle the same loop, but let's do it this way. Yeah, I start from 0 and go to P num prox P++. So, and now just doing the output. Yeah, so let's do the output like this. We do standard output stream to the so putting the stream where we have this guy and we get the process number, then we take a closing bracket equal to and enter A of P, and then we stop this by standard end line. Okay, so this does the output, and after we are done with the output, I suggest, because we are well behaved, I suggest that what we have generated will delete. Yeah, will delete A. So, yeah, we'll delete A, and then we go to our, so then, okay, what we have done, we have read it, we did the output, and now we come to the else part. No, we received it, we wrote it, but we have not yet sent it. So the others, so those processes that have not rank 0, they are going to send stuff. And here using the standard just send without synchronous, yeah? Just send. So what are they going to send? They send my my new data. This is of size 1. This is an MPI. This is an MPI double. This has tag 0. No, sorry. That's not. This has destination 0, yeah, master process, and it has tag 0. And then it has MPI com world. So now we have sent this, done sending. So what is missing? There are two things that are missing before we end our program. Finalize. So MPI finalize. Sorry, that's different. Capital. Finalize. And then what? Okay, and then we have to do return 0 because there's an integer function. So okay, so let's save this. So that should in principle be what we are going to do. Let me try to compile this. MPI, now how do I call this? I call this ring.cpp, and I'm going to call this again ring. Okay, let's see whether it compiles, and it does not, because I wrote temp and I potentially wrote, okay, I wrote TMP here, and then I wrote temp down there. So I have to correct this and then try to compile this thing, try to compile this thing again. Now it compiled. Did you get a compile?
I'm still in.
Okay, so we are, so where are you?
At line 32.
At line 32, okay, yes.
STVM.
Okay, 32. So you do the output, yeah? Yeah, so we delete A and then we do the sending back, the sending of all of them. So you see, we have to do the receiving in a loop, but the sending is not in a loop. Yeah? So because all the others send only once, while the receiving part is receiving everything. So in principle, we could, of course, use here already the gather function, right? But we did it by hand. So there's always different ways doing the same thing. So once we later have this, put this into brackets. I don't know why I'm not doing this. Okay. Then you can try to compile, right? With MPI C++ ring or whatever you called it. And see whether you get it compiled. Now if you have a typo in it, then it may get stuck. If not, yeah, you have to go to the right place, of course. No, you're already in PBR 2050. You have to see, go through where you have your, no, you're, yes. So, I guess you have to go into this folder. You don't need to type it. Here, go this. Makes it faster. So, and are you now in the right place or are you at a subfolder?
Yeah, I'm right place.
So then you use this MPI C++. Yeah, your file name, your -o, the output name. So you have a compilable version. Undefined reference to main. Okay, we've already had this problem before. So why RC, R3, blah, blah, blah. Okay, you can try to put this here. I don't think that makes a difference. Let's try it out. I mean, it did not make a difference for me.
Yeah.
Okay, now that's confusing. But this is not the thing that I wanted to try out. Okay, let's be confused, yeah, because there's another, we wanted to do something else now, yeah. Let's say we got this compiled and we try to run it with MPI run -mp4 ring. So, okay, I'm doing this, and what I observe is that this program gets stuck, right? So what I'm going to do is now I'm using Control C to stop it. The reason why it is stuck is because I use the synchronous communication. I'm using the synchronous communication. So sending basically the problem that we have is, let me go up here. So I'm sending, then I'm waiting to receive something, but my neighbor is also sending and is waiting to receive something. Yeah? So there, so this is what we call a deadlock. the easiest way, but this is not a clean way, to kill this deadlock is by using, instead of the synchronous send, just the send. Yeah, that's not a clean way. This may work or may not work, but I'm going to try this out. I'm removing one S, so it's very simple. I'm removing one S and try to compile this again, and then run it again, and then I actually get some nonsense. I get some nonsense result.
I still get
Okay, you get the same result.
like earlier, stuck somewhere. It's not getting any outputs.
So it's not working even. Did you save it?
Yes, I saved it.
Okay, so that's not a clean way to break this deadlock. Do you have an idea how we could break this deadlock in another way? Any suggestions? There are two solutions to this problem that I know of, or that come to mind. One is a rather bad solution. Okay, what is our time? Do you have an idea, or should we get to no idea? Okay, okay, so this is our problem, right? There is, so we get deadlocked. So there is one solution that I suggest we are not doing, because it's again not a clean solution. And this is by by breaking the ring. Yeah. So what you could do is you pick out. Actually, we could also implement this. So the problem is that all of them try to send first and receive second, right? So we can break the ring by saying that there is one process that receives first and then sends. Yeah. So let's do this. And okay, so I'm going to return this to synchronized send as synchronized send, and let's just do the following. I use if my ID is not equal to 0, I do this, right? And else I do it the opposite way. So now this I do it the opposite way, so okay, I have to exchange this. I will first receive, and then I will send. Okay, I save this. I compile it, and then I run it. The thing is, I don't Konstantin, can you tell me why I get this strange result here? 2.3 e minus. Okay, so this is something that I did not figure out. So my old data is my ID. Do I have to cast this? I mean, this is an integer and this is a double. I was thinking that I put. Okay, I have somehow. I mixed up something else. Okay, I mixed. So this was a typo, obviously. So I get. My new data. I don't know why we get this strange outcome here. Something. Well, I was thinking that I temp. Okay. I think I know what mistake I did, because I did not. Okay, so I see. AP is equal to temp. So this is, I did not, okay, good. I did not initialize it. Yes, but it's temp, not. Okay, so this is, I have to run this again. Okay, did you see what the mistake was? Yeah. So, okay, I compile it again and I run it again. So, okay, so that we get to the neighbor. But this is not. So why is this not a good solution? To break the ring. It's not a good solution because this deadlock is still everywhere on the ring. It's just that it is broken in one particular place. So all of them are still waiting until all the stones fall along the ring. Yeah? So we don't see this because our ring is very small and we don't have to wait for a long time. But this is not a clean solution because the last one has to wait for everybody else. So how do we change our problem in such a way that they don't need to wait for everybody else? Well, this can be done by breaking the ring not in one place, but by breaking the ring in every second place, right? So taking every second place to break the ring, and going back. So here I'm in the wrong place. So what we should do instead of breaking the ring only in position 0 is to see whether we are in an odd or an even rank. So this is something that we can do by using the modulo operation. So you use my rank modulo 2, and now this will distinguish between odd and even, whether it's 0 or 1, right? So we do my ID modulo 2, save this again. Of course, we are not going to see a difference in performance because everything is so small though that it will perform in the same timing, but this is the correct way we are supposed to do it. We run it, and yes, of course, we get this expected result. Okay. So this basically is what we wanted to do today. Do we have any further? Wait. Okay, I'm going to close the recording and then